Thanks, Ben. It's really fantastic to be back here. I'm excited to see a lot of new faces and many familiar faces as well, and to be in this room where I attended many of these talks as a student and gave a couple as well. So it's very nice to be back. Getting into my talk, the title of the talk that I'm going to give today is Not So Fast, Revisiting Assumptions in and About Natural Language Reasoning. So the context for this talk is systems and data sets and tasks that are designed to enable reasoning about real world situations in the form of natural language. So in a natural language reasoning task, we might have some description of a context or a situation, such as a sentence like somebody dropped a glass on the floor, followed by an inference like the glass shattered. So in the standard natural language inference setup, we would have to apply a label to this inference. So in this case, the label of the glass shattered would be neutral. It's not entailed because it's not, strictly speaking, necessarily the case that the glass would shatter. It's not contradicted. We just don't have enough information to determine whether or not in this scenario the glass shattered. But there are other approaches that we could take to applying a label to this inference. We could also take a more graded approach to the likelihood of the inference. We could place it on a ordinal scale of subjective likelihoods, or we could place it on a linear scale. We can also take an approach to reasoning in natural language that takes a generative approach, where we give a system an input that is a description of a situation, and then rather than applying a label to an inference, whether it's entailed, neutral, or contradiction, the system generates an inference about what is likely to be true in that situation. So this is an example. As an example, this is what the COMET system is trained to do. So that's the context of this talk. I'm going to be talking about systems that reason about real-world situations through natural language. So to give an overview of the talk, the main theme here is I'm going to be talking about the kinds of assumptions that these systems make, as well as some assumptions that we as researchers make about these systems that may not necessarily be true. So in the first part of the talk, I will talk about the ability of these systems to override assumptions that they make through defeasible inference. So this is the scenario where a system has received some information in the form of context, like somebody dropped a glass on the floor, then makes the inference that the glass shattered, and subsequently obtains new information that calls into question the original inference. So what if we subsequently learned that the glass was dropped onto a soft shag carpet? That kind of new information would undermine the inference that we originally made. So this is the task of defeasible inference that I'm going to talk about. The second part of the talk, I will discuss some assumptions that have been made about the implications of partial input baselines. So there's been work showing that when you train these kinds of reasoning systems on just one part of the input, so often in NLI, that would be just the hypothesis, that you can get accuracies that are above what you would expect at random. And so this calls into question the ability of these systems to actually do the reasoning task that they're intended to do. And so I'm going to revisit the assumptions that we make about the reasoning capabilities of these systems based on evidence from partial input baselines, and talk about some experiments relating to that. And the third part, I will talk about, if we have time, some kinds of assumptions that these models make that are actually harmful because they involve social stereotyping, making assumptions about individuals involved in the situations described based on their social identity. And in particular, I'll be looking at the case of generative reasoning models and cases where those generative reasoning models produce stereotyped inferences. Okay, so the first part I'm going to talk about defeasible inference. So a classic example of defeasible reasoning is we have a premise like Harold is a bird, And from that, we infer that therefore Harold flies. But if we subsequently learned that Harold was actually a penguin, we would have to revise that original inference and conclude that Harold therefore does not actually fly. So this is a classic example of defeasible reasoning. What does the word defeasible mean? The definition is capable of being annulled or made void. So when we think of defeasible reasoning, when you think of the word defeasible, think of the word defeat, as in to defeat an argument. So why do we care about defeasible reasoning? I'm going to argue that defeasible reasoning is actually ubiquitous across many different domains of reasoning. So in scientific reasoning, we have this nice quote from Armstrong, 1983. The laws of nature are oaken, not iron. They have exceptions. So mammals give live birth. This is a generalization from science, but we have exceptions in the case of monotremes, like echidnas or platypuses, which lay eggs. Newton's laws of physics, force equals mass times acceleration, is generally true, except it doesn't hold up when we're talking about systems moving at relativistic speeds. When we're talking about reasoning about the physical world around us, the kinds of common sense knowledge that we need to reason about the physical world, those kinds of reasoning are also subject to defeasibility. So if Pat drops a drinking glass, it will break when it lands. That's sort of a general inference that we would be able to make. But again, there are exceptions to this. So this would be less likely to be true if the glass landed on top of a soft pile of clothing. Wet surfaces are generally slippery to walk on, but less so if you're wearing rubber-soled shoes. And similarly, if we're talking about reasoning about social interactions in the world, what kinds of rules govern social interactions, these social rules are also subject to exceptions and defeasible reasoning. So in certain cultures, it's customary to greet people by shaking hands. But in the past couple of years, we've learned that that may not always be the case during a pandemic. Another example is it's rude to not show up to a wedding that you agreed to attend, but everybody understands that there can be exceptions. If somebody becomes ill, they might not be able to attend, and it's not a breach of social expectations in that case. And in the domain of legal reasoning, most laws have some forms of exceptions. Sometimes these are intentional, sometimes they're unintentional in the case of loopholes. The applicability of various laws may depend on context. So in most legal codes around the world, it's illegal to kill another human, although it may be permissible in certain cases of self-defense. Okay, so with all that in mind, I'm going to turn to developing a task for defeasible reasoning. So as we saw, most NLI datasets most natural language inference datasets are set up in the form of, we have these pairs of sentences. The first sentence is a context or a premise that describes a situation. The second is an inference that may or may not be true based on the context. But what these datasets tend to lack is any additional nuance about the kinds of circumstances under which those inferences may be more or less likely true to hold up. So we could augment these NLI context inference pairs with the kind of information about the contexts in which the inference is less likely to be true. So the glass shattered is less likely to be true if it fell on a pile of laundry. It was dropped only an inch from the ground. It's made of durable glass. This whole situation is taking place on the moon or the International Space Station. And in contrast, the inference is more likely to be true if the glass is made out of particularly thin material. It's dropped from a rooftop. It lands on concrete if it was already cracked. So these are the kinds of additional pieces of context that would help systems make more nuanced inferences given additional context about a situation. So we're going to define a defeasible reasoning task where we're going to augment these existing natural language inference data sets or inference style data sets with these additional pieces of context. So this is work that I did well at AI2 with my collaborators there and the University of Washington. So we developed a definition for this defeasible natural language inference task. This derives directly from or is very much inspired by the kinds of definitions that we see in tasks like recognizing textual entailment or natural language inference, where inferences are based on the kinds of inferences that a human would make reading these sentences. So we say that given a premise P, we say that a hypothesis H is defeasible if there exists an update sentence U that's consistent with the original premise, such that a human would find H less likely to be true after learning this update U. So there can be two kinds of updates that we characterize here. So we'll call an update a weakener if a human would most likely find H, the hypothesis, less likely to be true after learning U. And in contrast, if they would find the hypothesis more likely to be true, then we call the update a strengthener. So these updates can either be strengtheners or weakeners, depending on if they make the inference or the hypothesis more or less likely to be true. So we construct this defeasible NLI data set, or also we call it delta NLI for short. So you can think of delta as in sort of the change in confidence of the inference. And so to reflect the fact that defeasible inference is ubiquitous across many different kinds of reasoning domains, we're augmenting 3 different kinds of data sets. So the first is the Stanford Natural Language Inference data set. The second is a common sense inference data set consisting of if-then common sense reasoning pairs called atomic. And the third is a data set of social rules called Social Chemistry 101 that has generalities about social norms. And so the augmented versions of these data sets are called defeasible SNLI, defeasible atomic, and defeasible social rules, or delta for short. So the approach that we take to generating these update sentences of both weakener and strengthener type is we take the context inference pair from the original inference data set, and we present those to a crowdsourced worker who then has to write one sentence that acts as a weakener and one sentence that acts as a strengthener. So in this case, they might write as a weakener, the glass fell onto a pile of laundry, and as a strengthener, they might write that it landed on concrete. And this protocol, you may not be surprised to find, will result in certain artifacts that we'll talk about later. And I'm happy to talk more about sort of the reasons why we chose this protocol to begin with. But this is the approach that we have taken. So the resulting data set has a roughly 100,000 update sentences for the SNLI data set, 100,000 update sentences for the social chemistry data set, and about 50,000 for the atomic data set. And these are roughly weighted 50-50 between weakeners and strengtheners after we do some validation on the sentences that crowdsourcers wrote. Okay, so to give some examples of the kinds of data that we have in this data set. So for the defeasible SNLI portion of the data set, we start with an original example from SNLI. So the premise is 2 men and a dog are standing among rolling green hills. The hypothesis is the men are farmers, and the label is neutral because we can't conclude for certain either way if the men are farmers. So the weakener that the annotator here wrote is the two men are wearing hiking backpacks. So this would tend to undermine the idea that the men are farmers because it suggests instead that they're travelers or backpackers. And the strengthener that was written is the dog is a sheepdog, which I thought was a cute example. It's a little bit circumstantial, but I think a little bit of circumstantial evidence, but I think that it still reinforces the idea or strengthens the idea that the men are farmers in this example. For the defeasible atomic data set that we augmented, the original atomic data set is a set of if-then reasoning patterns that take a brief description of a situation with a generic participant, such as person X is sprayed by a skunk, and then pairs that situation with a bunch of different inferences about that situation along different axes or dimensions of reasoning, such as what happens as a result, what happened before, how do people feel about the situation, and so on and so forth. And so in order to augment this data set, we're going to take the original situation description as our context, and we're going to select one of these branches of inference at a time. So our original sentence here is person X is sprayed by a skunk. That's our context. We'll select one branch. As a result, person X feels smelly as the inference. And so for this context inference pair, the annotator wrote as a weakener, person X is wearing a protective smock. That means maybe they're less likely to feel smelly. And as a strengthener, many people are pinching their noses around person X. And finally, for the defeasible social rules, as an example of the kind of social rule that's present in the social chemistry. Oh, Jason, do you have a question?
Yeah, I was a little surprised by the strengthener there, because I had been imagining that strengtheners were causal as opposed to evidentiary.
Yeah, that's. Yeah, some of them, it's not entirely the case that, so we didn't specify that the strengtheners or weakeners had to be causal in nature. It's just a human reading this sentence would be likely, more or less likely to conclude that the inference is true.
Yeah, so you didn't mind getting.
That's right, yeah.
Did you get a lot of it?
We didn't measure how much are evidential versus causal. So that would be something interesting to look into. I don't have an answer for that. Okay, so for the defeasible social rules, the original data set consists of social rules like it's okay if you don't like the food someone gives you and you don't want to eat it. And note that this is not a context inference pair of two different sentences, but rather the if-then relationship is kind of implicitly smushed into a single general rule. And so the weakeners and strengtheners that the annotators are writing here are instead about the sort of context in which the rule is more or less likely to apply. So the weakener for this rule is you told them you would try some, and the strengthener is you're allergic to the food. So it's especially okay to not try the food if you're allergic to it. Okay, so we, given this data that we collected, we developed a binary classification task. So given a premise, hypothesis, update, 3-sentence tuple, the task is to predict whether the update acts as a strengthener or a weakener in the context of the premise and the hypothesis. And so a majority baseline gets 50%. The human performance is roughly 80% on the task. And what we see here is that a full input model, this is a fine-tuned Roberta model, achieves very close to human performance on this task. We have also experiments with partial input baselines where we provided the update only or the hypothesis and the update excluding the premise. And what we find is that the update only models do perform above the majority class baseline, but are substantially below the full input models. The hypothesis plus update model is a little bit behind the premise, hypothesis, and update model, but only by a little bit. And so this suggests that once you have the hypothesis and the update, adding in the premise doesn't really add that much additional information. And one possible explanation for this is if we think about what the defeasible reasoning task is like, thinking back to the original example that I gave about Harold as a bird, the update sentence that we have in that example is that Harold is a penguin. And so once we know that Harold is a penguin, that update actually entails the original premise in that classical defeasible reasoning case. So we don't actually need to know the premise in that particular case. So in general, once we have the hypothesis and the update, the premise is a little bit less important to know. So rather than taking the approach of trying to make this task much harder as a classification task, instead we chose to focus on turning the data set into, using the data set to create a generative defeasible reasoning system. So this would be a kind of system that we might, in theory, be able to apply to arguments to find weaknesses in arguments or exceptions. I think in general, the ability to generate these strengtheners and weakeners is kind of an interesting direction. So when we fine-tuned a conditional language model, so we fine-tuned GPT-2 on the data that we collected, it was able to make various interesting strengthener and weakener generations. So just to give some examples here, from defeasible SNLI, the original premise and hypothesis that we fed the system was a surfer is riding the waves while another surfer sits on his board waiting. The hypothesis is there are people surfing in a competition. So this is a neutral entailment, or a neutral hypothesis rather. And the strengtheners that were generated by the model were the people are wearing numbered bibs. There are judges watching the surfers. So both of these would tend to increase the strength of the hypothesis that the people are in a competition. And the weakeners were the surfer on the board looks bored and the surfer on the board is a beginner. An example for generative strengtheners and weakeners from the social rules is we gave the social rule input, it's wrong to ditch your friends. And the strengtheners were, they need your help, they're stranded in the middle of nowhere. The weakeners generated were, they're taking advantage of you, you have to go to the hospital. So in general, the system is able to generate valid strengtheners and weakeners in many cases. We did a little bit more of a systematic evaluation of the generated outputs. So when we evaluated the human written strengtheners and weakeners, they got about 80%. On the generated outputs, the accuracy of the strengtheners and weakeners were closer to 60%. And we also trained a hypothesis-only generative model that did a little bit worse than the full input generative model. So some generalizations about, and one thing to note here is that this is, oh yes, there's a question. Oh, great, thank you for asking. So the reason why this particular, so we're missing the hypothesis only version for Delta Social because Delta Social only has one input sentence. So we don't have a separated context and context inference. So we only have one model for that. Yeah. Okay. So looking at generally the quality of the strengtheners and weakeners that were generated, we find that in general, the strengtheners and weakeners are topical and fluent. The systems are able to produce many effective strengtheners and weakeners. And this is something that's difficult to do accidentally. A completely uninformed baseline wouldn't be getting, you know, even close to 50 or 60%. It would be closer to 0%. Some of the bad news is that occasionally we observed that strengtheners and weakeners were actually swapped. So sometimes the model has a little bit of difficulty conditioning on the right label. Sometimes the weakeners contradicted the premise, which was an instruction that we gave to crowdsource workers to not do. But sometimes the models generated weakeners that were contradicting the premise. Sometimes strengtheners just reiterated the hypothesis or presupposed the hypothesis, which is also a violation of the task formulation. One thing that we observed that's kind of questionable behavior, sort of interesting behavior, is that we saw sometimes these models were defaulting to broad purpose weakeners. So in the case of social rules, a broad purpose weakener might be something like they were mean. So we see that in the case of, you know, the cases where a social rule might be less likely to apply is when someone else is already violating other social rules. So these aren't incorrect weakeners, but they are sort of strategies that the system might back off to when it can't come up with something more specific. And one open question is, how well do the generations that we're able to create from these systems actually cover the space of all possible strengtheners and weakeners? And I think that's a challenging question to think about in future work. So one question that I think is raised by some of, yes?
Do you guys look at how we generalize vertically, whether it was performance, whether it was attack based, generalizing to a rule, a general rule, like in some examples, something like either generalizing the idea that someone would think smell bad, versus where I'm cause effect.
I'm sorry, I'm not sure. I totally follow.
Do you have a sense of whether the model's performance is generalizing, like look at whether it's capturing higher order, more abstract rules, so things like this the general social rule that or the general rule that if you're making smell bad, like you might want to be in the situation rather than the fact that you were caused to smell bad for them. Like, are you going to test that? Or are you going to actually say like ask questions?
Yeah, we haven't looked at sort of the generalizations of like whether the system is like thinking about examples in a very specific sense or applying like broader
Like, if you were to say something like a person made the offensive people around them, and so they decided that like something at a higher order than they were sprayed by a skunk versus they were made smell bad versus they were made uncomfortable with the way they were in versus I'm pretty more generalized vertically like that rather than transferring others in what situation.
Right. Yeah, I don't know. That's a good question. I think one thing that we're thinking about, I don't know if this is related to what you're asking about, but thinking about the various implicit variables that are present in the kind of reasoning problem. So dropping the glass, you could come up with a bunch of weakeners that have to do with the height that it's dropped from or the kind of material that it falls onto.
Right. Yeah. Like generally any straight person break hole.
Yeah.
Or like I want to whether it's whether the way they that general thing that by the model or whether
yeah, we haven't done any experiments in that vein, but that's an interesting idea. Everything right now is kind of more example and data oriented, but I think that would be interesting to try to suss out the sort of more generalities that the system might be learning. Yep. The by looking at an update only model, yeah, I in some ways that may sort of get at sort of what the priors are on what yeah, if an update is likely to act as a strengthener or weakener, but yeah, that's an interesting point. Yeah. Yeah.
How does the model become clever enough to distinguish between the patterns in dataset versus
right? Yeah, that's actually a great point. So we defined the task in such a way that we don't actually have labels that cover the total possible space of update sentences that we could encounter. We just had annotators write update strengtheners and weakeners, but not all sentences would fall under that category. So the model behavior in that case is not actually well defined, and that would be an interesting experiment to run. Okay, so I'm going to move on to part 2. Actually, I need to go over this slide. So one question that is raised from this data is, we see that the partial input baselines here are having, much better than a majority class baseline performance. And so this could raise doubts about whether or not these systems are actually learning to do the defeasible inference task as defined. But we also see that from the data that we collected, we're able to train a generative model that is seemingly capable of doing some form of the generative reasoning task. So what kinds of reasoning are the models able to learn from the data? What's going on here? And so this leads us into the second part of the talk, where I'm going to revisit some assumptions that I think we've made about interpreting the meaning of partial input baselines. So we've seen that partial input baselines can show that natural language inference models are capable in some cases of ignoring context, but we want to know, do they actually ignore that context? So this is work by my PhD student Neha Srikanth at the University of Maryland. So to give some quick background, again, natural language inference is the task of deciding whether a human reading a premise would infer that a hypothesis is true. And so one assumption that I'll just grant for the purpose of this conversation, I think we could have an interesting discussion about whether or not this is true, but I'm just going to grant it, which is that answering the NLI question, applying an NLI label should require a system to use both the premise and the hypothesis. If it's not, then maybe we'll just say that it's not actually doing the reasoning task as intended. And so simultaneous discoveries in 2018 were that when you train a NLI model on the hypothesis only, you see a higher performance than a random baseline or a majority class baseline would get. And so this sort of suggests that there might be spurious correlations or artifacts present in the hypothesis that allows the model to predict the correct label. So what are the takeaways from these partial input or hypothesis only baselines? One is that the hypothesis only baselines are learning to leverage dataset artifacts that are hinting at the correct answer and are thus able to make correct predictions without doing the intended reasoning task. The second conclusion that people might draw is that therefore full input models trained on both the premise and the hypothesis are doing the same thing as the partial input baseline models, that they're exploiting artifacts present in the data set to make the correct prediction rather than doing the intended reasoning task. And this would be a bad thing. So I'm going to call into question this second conclusion, this assumption that some people might make about the reasoning abilities of these models based on the partial input baselines. And ask, is this actually a valid conclusion? And I'm going to argue that it's maybe not such a valid conclusion. So I'm going to present an analogy to a math test. So suppose a teacher has developed, written many math tests over years. These are IID math tests, and we give the math tests to one student to study from, but we remove the questions from all of the multiple choice answers. We just show them the multiple choice answers, and we ask them to sort of study the patterns present in the tests. And so when we give them a test, a new test to take that also doesn't contain the questions, just the answers, they're able to perform above random based on observing things like, well, maybe answer C is more likely than answers A or B. Maybe even numbers are more likely to be the right answer than odd numbers, and so forth. And we give a second student all of these tests to study, but the second student gets the full question. They get the question and the answers. And so they study the test, and then they take a full test with questions and answers, and they're able to do much better because they're able to actually perform the math that's involved to answer the question correctly. And so I think the part of the fallacy involved in the second conclusion that full input baselines are doing the same thing as partial input baselines and learning to cheat or leverage these artifacts is not necessarily the case, because it could be that there's a better strategy to perform well, which is to just actually do the reasoning problem given the information that's available. So the question we're going to ask here is, do full input NLI models learn to condition on the premise despite being trained on data sets that contain artifacts? And I'm going to modify that question and replace the premise with context, because we're going to talk about two data sets here. One is SNLI that contains premise hypothesis pairs, and the other that we'll look at is the delta SNLI data set, where the context, we'll call the context the premise and the hypothesis, and we'll call the target in the case of delta NLI the update. So we're going to now redefine, instead of premise and hypothesis, we'll talk about context and target. So context for SNLI is the premise, context for delta SNLI is premise and hypothesis. Target is now the hypothesis for SNLI, and target is the update for delta NLI. And so the partial input model will be trained on the target only, and the full input model will be trained on the context plus the target in these experiments. Okay, so a couple caveats to note. One thing is that conditioning, if we're just going to try to show that these models are conditioning on the context. So this is not necessarily a sufficient condition to conclude that these models are doing reasoning It's just a sufficient condition to reject the assumption that they're not doing reasoning on the basis of ignoring the context. Okay, so we're going to investigate this question through two sets of experiments. The first is we're going to ask, does access to context strengthen a full input model's confidence in the correct label as compared to the confidence of the partial input model? And to give away the answer, yes, we find that full input models are more confident in the correct label than partial input models. In the second set of experiments, we are looking at modifying the context. So we're going to take examples that we think are likely to contain artifacts, and we're going to modify the context and see whether or not the system is able to switch its label to the correct label when the correct label has actually changed based on modifying the context. Or if it's not able to switch its label, then we would conclude that it's being over-reliant upon the artifacts that are present in the target. And we find here that yes, also in this experiment, full input models are sensitive to context modifications that change the label despite the presence of artifacts. Okay, so the first experiment, we're asking, does access to context strengthen a full input model's confidence in the correct label compared to the partial input modifier, compared to the partial input model's confidence? And so this scatter plot shows each point in this plot is one SNLI test example. The x-axis is showing the partial input model's confidence in the correct label. So the further to the right a point is, the more confident the partial input model was in the correct answer. The y-axis is showing the confidence of the full input model. So the higher up a point is, the more confident the full input model is in the correct answer. And so the fact is that any points that are lying above this red diagonal are examples where the full input model was more confident in the right answer than the partial input model. And we see that the vast majority of the density lies above the diagonal. So in most cases, the full input model is more confident in the correct answer than a partial input model. And you can also see here the marginal distribution of confidences in the correct answer. So we have sort of a greater degree of the partial input model is informed to some extent, but the full input model is much more confident in the correct answer than the partial input model. We did a similar experiment with, was there a question? Yeah.
I was looking at one we're thinking about like bottom right there's something about the
yeah, we actually that's a great question. We haven't sort of analyzed the examples that fall below. We would expect by chance some of them to occur below that, but we didn't do sort of a more extensive exploration of what those points below the diagonal actually are. Yeah. Yeah. Okay. That's very possible. But in this case, we're looking, if that's the case, then that would be because the longer context is actually helpful for the model to predict the correct answer, because we're looking at we're not just looking at the model's confidence in the most probable, in the answer that it thinks is most probable, we're looking at its confidence on the correct answer. So if that's the case, then that's because the longer context would actually be helping it get the answer right. Yep.
First, I'm not familiar with multi-MNLI data. Are all of the hypotheses?
So in SNLI, what do you mean by that?
So there are two servers on for forward.
Mm-hmm. Yeah, I mean, so the way that NLI original data set was SNLI was constructed, I think constrains the annotators to be talking about the situation that's described in the original sentence. It could be that there's multiple entities that, and the resolution could be ambiguous. I'm not sure exactly what the impact that would have on artifacts would be here.
And then the other version of this one. So the match terminology kind of pointed out that there are particular components of the context that might be specifically inductive bias. For example, if I thought export expression might be so I'm wondering if there's like some version of like keyword extraction or like recognition type annotation somewhere on the spectrum between full context where it's not actually the full context, it's recognizing that
Yeah, I mean, I think now we're getting into sort of the gray area of like what's a spurious correlation, what's an artifact, and what's actual reasoning, because you know, if you're looking at some sort of shallow features of the context, maybe those are reasonable to actually include in your reasoning process. Yeah. Yes. The partial input model on some of these performs better than a majority class baseline. This is a three-way classification problem.
Okay, but is it better? But like if it's better than random classes, then I think best increase confidence will then still make the full input model confidence more likely if you just increase the confidence on one thread.
Let me see if I understand. If you increase the confidence on,
like if the partial input model is 60%, and then you just increase the confidence on all the ones that got right, and on all the ones that got wrong, you also increase the confidence. Well, then overall, you'll still increase the confidence on the ones that got right more than the ones that got wrong. And so it'll still look like the confidence, but actually you're still going to count. But I think maybe the right thing to do is look at one of those examples where the confidence was like, I think if you use the partial input model and I don't know, maybe you can filter that so that some of them.
Yeah, I'm not sure. I think, I mean, what we're looking at here is the confidence in the correct label, not just the confidence in the most likely label. But so yeah. Yeah. Yeah, I think I'm going to have to defer this to the end. I do want to discuss this more, but I have a little bit more to get through. But it's a great question. I think I just want to set it aside and we'll come back to it. Yeah. So what we're seeing here in the defeasible NLI is also a shift in confidences that the model is more certain that the right answer has greater confidence in the correct label. And we see also a similar shift in the marginal distributions. So the second experiment that we ran is to test whether full input models are sensitive to context modifications that actually flip the label. So we're going to select premise hypothesis pairs in the case of SNLI, or premise hypothesis update pairs in the case of delta NLI, that are likely to have artifacts present because we filtered for examples that a simple lexical model gets correct, or a hypothesis only model gets correct, or a partial input model gets correct. So examples that are likely to have artifacts we go and modify the context so that the correct label is actually different now after modification. And we look at the accuracies of the system trained on the original data set, how it performs on these modified examples. And so for SNLI, we have the results broken out by label switches. So we have 76% accuracy on examples that were originally entailed and then after modification became neutral. And so in general, we're seeing overall pretty high performance on these context edited examples. The one notable counterexample is in the case of neutral. When we change the neutral examples to entailed, we find that the overall accuracy, it's still capable of flipping its label to entailment about 42% of the time, but there could be some substantial artifacts influencing the performance in that particular case. But in general, we're seeing the models are capable of flipping the labels. And we see a similar trend in the delta NLI data set, where we get about 76-75% accuracy when we switch from weakener to strengthener or vice versa. So the key takeaways here is that one, it is hasty to conclude that models trained on data sets with artifacts are not capable of reasoning, even though high-scoring partial input baselines show that full input models could ignore context. These experiments show that they don't. They can leverage the context effectively. Secondly, of course, artifacts can and do lead to models with exploitable heuristics, but artifacts don't necessarily spell disaster for a model's reasoning capabilities. Thirdly, NLI models can and do meet one of the necessary conditions for reasoning, or a condition that we're granting as necessary, which is leveraging the full input. And finally, partial input baselines should be understood as warning signs. They're sufficient to conclude that full input models might not be leveraging critical context, but insufficient to prove that they don't. Okay, and so for the last part, I've only got a few minutes left, so I'll try to get through this quickly. I'm going to talk about cases when these reasoning models make harmful assumptions about people based on social identities in the form of social stereotypes. This is work with my collaborators, Trista, Anna, and Hal at the University of Maryland. And so we're looking at the case of generative reasoning models, where we give an input, a short description of a scenario, and we have the system generate an inference as an output. And so we're going to create a bunch of controlled inputs to the system. So these will be situations, sentences that involve one person of a particular identity involved in one of a set of possible situations. And so we're going to take the cross product of these identities and situations and look at the kinds of inferences that are generated by these systems. So these identities are different gender, race, nationality, religion, political identity, and socioeconomic status. And so what we find is that given a single situation, such as a person makes money, if we alter the identity of the person involved in that situation, the inferences that the models make are strongly dependent upon the identity of the person. So if we give the example of a Jewish person makes money, the hypothesis that's returned is Jewish people make money because they have a lot of money. This is a negative stereotype about Jewish people. A poor person makes money. The hypothesis returned is a poor person makes money by selling drugs. This is a negative stereotype about poor people as criminals. So we see a lot of problematic inferences that these systems are making that are dependent on the identity of the person involved in the situation. In order to do some sort of systematic evaluation of these generated inferences, we perform a manual evaluation by answering various questions about the generated inferences. And so we ask a number of questions. Is the hypothesis plausible? Is the hypothesis based on the person's identity? Is the hypothesis based on the situation? Does the hypothesis express positive or negative sentiment towards the person? Does the hypothesis invoke a known stereotype? And if so, to describe it. And so the four of us who were working on this project, we each annotated a fairly large number of examples. And we expected to have actually relatively low agreement on whether the hypothesis invokes a known stereotype. It's known that it's actually quite difficult to get agreement on these things because there exist, differences in people's knowledge or awareness of different kinds of stereotypes. But we found that we were actually able to get somewhat higher levels of agreement when we asked instead, when we tried to answer the question instead, is the hypothesis based on the person's identity, where we had 39% agreement. And these are just raw agreements numbers for when all 4 annotators agreed on exactly the same label. So there's a lot more analysis in the paper that goes into detail about the various kinds of patterns that we observed in the data. But to just show one example, we looked at the kinds of identities that were most likely to result in inferences that were based on identity alone. So these were inferences that annotators said were based on identity, but not based on the situation. And so formerly incarcerated people, Asian, Jewish, Democratic, Irish, homeless, these were groups that across all of the different social categories that we looked at were most likely to result in an inference that was based purely on the identity of the person involved in the situation alone. So I think that this leads to an interesting possible direction for future investigation, is thinking about stereotypes as a form of defeasible inference. So if we have systems that are capable of overcoming assumptions that they make based on updated information, could we treat stereotypes that these systems are producing in a similar way by feeding these systems information that would tend to weaken the stereotyped inference? So if we have the example of a poor person makes money and it assumes that the poor person makes money by selling drugs, can we defeat that stereotyped inference by providing additional updates such as the person earns money at a job, the person is not a criminal, the person pays income taxes, and so forth. So I think that's maybe an interesting possible direction for future investigation. So some takeaways here. So I talked about defeasible reasoning as an approach to better context-sensitive, more nuanced reasoning with potentially broad applications across different domains. Secondly, we saw that partial input baselines should be seen as a red flag, but not necessarily a final verdict on reasoning abilities of models. And thirdly, generative inference models are overly sensitive to identity and often produce stereotyped inferences. So I'm going to end there. If we have any, I guess we're sort of low on time, but if any final questions people have, I'm happy to take them.
I guess the third part, did you try the intersection of demographics and what you expect?
Yeah, we had some follow-up work where we looked at the intersections of identities, and I can point you to the particular paper. But yeah, I think that is actually an important sort of step that this kind of research needs to look at, is how the stereotypes or the differential treatment is impacted not just by individual identities, but the intersections of those identities.
Has there been any kind of quantitative comparison of the stereotypes that generative models with human stereotypes?
Yep, that's the follow-up work that we did. We looked at we surveyed a bunch of individuals, asking them sort of their awareness of various stereotypes of groups, and measure sort of a correlation with language model stereotypes, or a measure of stereotypes that we came up with for language models from sentence completions. Yeah.
Are certain models better? This rate, so I think we're used to for
Yeah. It's a good question. I mean, so in general, you know, we obviously see certain models are just performing better at the task overall. In terms of their proclivity to produce produce stereotypes, you know, I think there's actually a connection with being over reliant on you know, artifacts. So we saw that these lexical models actually, we ran the lexical model on the context switched examples, and we saw that they got actually very low performance. So they are much more susceptible to artifacts. And so I think in some ways, actually, the same kinds of overgeneralizations that we see based on social identity may actually be, in some cases, mitigated by having stronger models that are less likely to, you know, use these sort of weak lexical co-occurrences, and they're actually acting in a way that's a little bit more defeasible in a sense that they can better condition on context and are less likely to overgeneralize.